Hi everyone. So today's lesson, the 27th of July, is going to be recorded. This is going to be on YouTube, and you obviously have the link to this. So it's going to be the same lesson. I'm just going to be doing a recap of yesterday's work. And then this is just because of the load shedding schedule. So hopefully this helps ease things out. So firstly, if we look at yesterday, what we've done, we basically kind of summarized the section for the gas laws. So we did a exam type question for this, where we looked at Boyle's law. So if you needed any notes from there, corrections, here is what we have done yesterday. And then we went on to speak about the other two laws. So we've got Charles' law, and then we also have Gay-Lussac law. And then these two laws are very, very same to how we've done Boyle's law. The only difference now is that you are changing different quantities. So here in Charles' law, we talk about the volume of the enclosed gas being directly proportional to the Kelvin temperature. So here we're changing the volume and the temperature. Okay, and then obviously we know that pressure will have to be kept constant. And then the most important thing is the equation that we have. So here we're going to be dealing with V1 over T1 is equal to V2 over T2. And the other important thing is knowing the shape of the graph. We will have a session where we go through some past year questions where we literally do these different laws. But if you understand Boyle's law and you understand the basic calculations, then Charles' law and Gay-Lussac law, it's exactly the same. It's just different values you're going to be substituting. So as I said as well, let's just quickly look at the Gay-Lussac law. So it's the same thing again. It's now that we are changing pressure and temperature, and constant is going to be our volume. And then this will be our graph and our important equation. P1 over T1 is equal to P2 over T2. So to summarize these three laws, we can draw this table here. A star basically means that these variables are kept constant. Okay, so if we look at Boyle's law, we know that we are changing the volume and the pressure, and temperature is going to be constant. If you want, you can actually just draw this in your book as well, and you can even add a column here where you include what the graph looks like. So it may be helpful when you're studying to remember that this is what the graph will look like. Okay, and then if we looked at Charles' law, in Charles' law we know that the pressure is constant, so we're changing the volume and the temperature. And in this case, our graph is going to be a straight line. Gay-Lussac as well, we are changing temperature and pressure, and volume is going to be kept constant, and we're also going to get a straight line graph. So again, what's important here is making sure you understand which law speaks about which two variables. Okay, because most of the time they're going to ask you to define that law, and you need to know if pressure is constant, then we're talking about Charles' law. Temperature is constant, Boyle's law, and so forth. So as I said, in one of the lessons next week, we'll actually go through a session where I'll probably give it to you to do as homework, a whole bunch of questions, multiple choice, and so forth. And then we'll spend a lesson just marking this, because this is a whole question in your exam paper. Okay, so that kind of wraps up the gas law section. You should be able to answer any three of those laws, Gay-Lussac, Charles, and Boyle's law, because now we've done all the theory, we've looked at the equations. There's only one more equation that I want to quickly mention, and as I said, next week we'll do a little bit more examples with this. I just want to quickly introduce you to it, and it is called the ideal gas law. Okay, so the ideal gas law goes something like this. Okay, we have PV is equal to nRT. And now each of these things stands for something. Okay, so if we're looking at this equation firstly applies only when you have an ideal gas. So only when you are dealing with an ideal gas, the question tells you you've got an ideal gas, then you can apply this equation. So what does all of these things stand for? P stands for the pressure of the gas. V stands for the volume. N, as we remember previously, it stands for your number of moles. Okay, and then we have R. R is a constant and it's called the gas constant. Okay, so we know about constants that it's basically just a number, and it's a number that goes something like 8, 3, 1, and so forth, joules, kilo, mole. So this will be given to you in your data sheet, so you don't have to remember that value. And then lastly, T is the temperature of the gas. And what's important about T is that T must always be in Kelvin. Okay, so we are used to always seeing temperature in degrees Celsius, but now whenever you have a temperature given to you in degrees Celsius, we must convert that temperature into Kelvin. Okay, and how do we do that? So in order to convert this, we obviously need to know what conversion unit to use, and so this is going to be important. So we know that okay, so even if you use 273, that's fine. You don't have to include the 0.15. But essentially what you're going to do is if you want to convert any value from degrees Celsius to Kelvin, then you are going to simply add, you're going to add this number, 273.15 Kelvin. So by doing this, you're going to change your answer from degrees Celsius to Kelvin. So just an example, what this might look like is, if I give you a temperature in 20 degrees Celsius, but I want to convert this to Kelvin, I'll take the 20 degrees Celsius and I'll add 273.15, and my answer here should be and now your answer is in Kelvin. So that's an important conversion step that you need to be aware of. Okay, so once again, we have this equation. This equation will be helpful when you have, let's count this. Firstly, there's 1, 2, 3, 4, 5 different quantities that you have in this equation. And how maths works is if I give you all 4 of these quantities, you can go and find the 5th quantity. So if I give you the pressure, the volume, the number of moles, and the gas constant, always we have that, you can use that to find your temperature. So that's how they will test you on this. So just a note on how are they going to test you on this. So how is it going to be examinable? So they might give you a question where they give you, this is just an example, they'll give you, so given will be your pressure. So you'll have your pressure, you'll have your volume, you'll have the number of moles, R you also know, and then they'll ask you to calculate temperature. So when you have a question with all of this information, then you should automatically remember that you've got this equation here, which should be given to you in your data sheet, and then you can go to that and you can calculate the temperature easily from there. So I'll try to look for a few examples for this, and then next week we'll do some practice questions with this, but it's not too bad, it's just applying the same equation here. And then just being aware that your temperature must always be in Kelvin, so this is an important thing to remember when you need to convert from degrees Celsius to Kelvin. Okay, so with that being said, I'm going to now move on to the next important thing that we're going to cover today. So at the very start of the lesson, not lesson but term, we started talking about Avogadro's law, and we started talking about the concept of what is a mole. So we're just going to do a quick recap of that, and then we're going to build on those concepts today. Okay, so if we remember previously when we talked about what is Avogadro's number. So Avogadro's number is a very special unit that we use. We use the symbol Na to represent Avogadro's number, right? And basically what it tells us is the number of particles that is present in 1 mole. So the number of, and the key word here is particles, and we'll explain what this means. The number of particles present in 1 mole. And remember, mole is just a unit of measurement. It's like how we use the number system and we say 100. In chemistry, we use this concept of mole. So we have 1 mole here. Now, particles is an important term that we use here because particles can refer to anything from atoms to molecules to ions. Okay, so we can basically describe any amount of atoms, molecules, ions, and so forth. And the special number for Avogadro's number is, and this number is also given to you in your data sheet. So remember in our first lesson when we talked about this, we said that the whole point of why we're using Avogadro's numbers, we can see it's raised to 23. It's a very, very big number. It actually is this number with 23 zeros following. So it's a very large number. And it's a good way of representing atoms. Because if we look at the real world, there's billions and billions of atoms in any object. So by using this number, we kind of make it more compact and we make it easier to express on paper. Okay, so just an example of how they might test you on this. If I were to say to you, how many okay, so I'm just going to get this question correctly phrased just so I don't confuse you. And these are typically your multiple choice questions, right? So or rather than saying this, let's just look at 1 mole of NaCl, or just sodium on its own. 1 mole of sodium. If we were to look at this 1 mole of sodium and we wanted to express it in terms of Avogadro's number, what we would do is we would say 1 times okay, so I'm going to stop there. We're going to just explain what this means. So what happens here is we are talking about a mole, right? So the mole becomes the particle that we're talking about. And if we've got 1 mole, then I just brought down that 1, and inside that 1 mole, we've got Avogadro's number in here, so Na, right? So essentially how you could think about this is you always want to look at the particles, so whatever that particle may be, times Na, which is this number here. That's how you express Avogadro's number. So if I told you you've got 3 moles of Na, then how would you express this? You'll say 3 times 6,023 times 10 to the 23. If I told you the particle is now 4 ions, then how would you express this? You would say 4 times 6,023 times 10 to the 23. If I used something else and I said 5 atoms, then how would we express it? We'll use 5 times 6. Okay, and then it's also good always after this to say what particle you're talking about. So in the first one we were talking about moles, then we were talking about ions, and then in the last one we're talking about atoms. So I hope you get the picture of how this works. Whatever particle you're dealing with, you take that number and you place it in front of that special Avogadro's number. They like to generally test these in multiple choice questions, so it's important to apply yourself now in the way that we're doing here. Okay, and then later on I'll give you a multiple choice question and we'll see how we do with that. Okay, so besides that, I just want to also refresh your memory on an equation that we did earlier on. And it looks something like this. So we said N is equal to M over capital M. So this was an important equation for the mass and moles, and it is going to become useful, especially when we start looking at calculations and equations. So we're just going to quickly remind ourselves of what this all means. So remember that N is basically your number of moles. Okay, small m is the mass of whatever substance you're dealing with, usually in grams or kilograms, and then your capital M we call the molar mass. And how do we get this value? Well, for this value we need to go to our periodic table. Okay, so recall that we would go to the periodic table, we would find the mass, and we would also need the chemical formula for it. Okay, I think the video is here on YouTube, so if you forgot how to calculate this value, make sure you refresh your memory and you know how to get that value. And just recall that if I give you the number of moles and I give you your molar mass, can you find your mass? Yes, you simply just use this equation. So this equation is all about you have at least two of these quantities and you can go ahead and find the third quantity. Okay, and then the next thing now we're going to talk about, which is fairly new for today, is something called the Avogadro's Law. So most of these things that we're going to go through today related to the gas, these are generally tested in your MCQ questions. But later on, we're going to also get to balancing chemical equations today, and that's going to become the basics for much of your larger questions in your paper. So all of it is really important, but what we're doing now, you won't really see a whole question in the paper. You'll see these more tested in your MCQs. So let's look at Avogadro's law, and I'm just going to write it from the guidelines. So Avogadro's law basically tells us that 1 mole of any gas occupies the same volume at the same temperature and pressure. At the same temperature and pressure. Okay, let's read this again and let's understand what they're trying to communicate by this. If you've got 1 mole of any gas, it's going to occupy the same volume at the same temperature and pressure. This law can be a bit confusing, but when we put it into practice in our chemical equations, it should make more sense. So just bear with me for now and just remember this important point, that if you've got the gas and this gas is occupying, or the gas rather is at the same temperature and the same pressure, then it's always going to have the same volume, right? So as long as you've got any two gases which is at the same temperature and the same pressure, then they are going to occupy the same volume. Those two things are important. But an extension of Avogadro's law comes in, and we have a very important thing up here. So we call this the standard STP. And STP stands for standard temperature and pressure, which is very different from same temperature and pressure. So do not confuse same temperature and pressure with STP. STP means standard temperature and pressure. Okay, now what this is, it's basically, these are it's a special condition, right? And what comes out of this is that if you've got 1 mole of any gas, it is always going to occupy this very special number now, which is 22,4 decimeters cubed. So decimeters is just a unit of measurement for volume, and it is the standard unit that we're going to use going forward. And this is at a special temperature of 0 degrees Celsius, and 0 degrees Celsius is 273 Kelvin, and also 1 atmospheric pressure. And this is equivalent to 101,3 kilopascal. So if you look at your guideline, this has exactly the same definition. We're just really just writing it out again. Okay, so let's firstly understand what this is telling us. STP stands for standard temperature and pressure. You can think of this as it's a very special temperature and pressure. Okay, and we know the value of the special temperature and pressure. So it has a value to it, and it's standard. And those values is, firstly, 0 degrees or 273 Kelvin, and 1 atmosphere or 101.3 kilopascals. So notice we're giving you two alternative units here. And what's so special about this is if you have these two conditions for temperature and pressure, then 1 mole of any gas is always going to occupy 22.4 decimeter cubed. That is a volume. Remember, this is a volume. So let's just rewrite this in a way that we can understand. What this law here is telling us is that if you have these conditions, so if you have a temperature of 0 degrees Celsius or 273 Kelvin and a pressure of 1 atmospheric pressure or 101.3 kilopascals. So notice this is that standard temperature and pressure. This is what STP means. Temperature is 0, pressure is 1 atmospheric pressure. Special condition. If you have these conditions for temperature and pressure, what you can conclude is that always 1 mole of any gas, so it doesn't have to be a specific gas, it can be any gas, but also it has to be 1 mole. So 1 mole of any gas is going to have a volume equal to, the volume is going to be equal to 22.4 decimeter cubed. This is what the law is telling us. So let's just rephrase that again. If you find yourself at STP conditions, what does STP mean? It means temperature is 0, pressure is 1 atmospheric pressure. Then 1 mole is going to always have a volume equal to this, 22.4 decimeters cubed. This is the special condition we're talking about. And now what happens is, we have a special name for this volume. Because it is a special volume, we're going to rename it. Okay, so if we look at this volume, because it is a special volume, we call it a special name. And we call it molar gas volume. Molar gas volume. Okay, so whenever you see molar gas volume, you're going to think again, it means STP conditions. And what it looks like is Vm equal to that same value, 22.4 decimeter cubed. Alright, per mole. So I don't want you guys to be confused with this. I just want to reiterate, STP means temperature 0, pressure is 1. That means that at 1 mole of any gas should have this volume. But our life becomes a little bit easier from here because we get an equation to represent all of this. And I'm quickly going to show you what this means in an equation form for a chemical equation. And then from there, we'll look at the equation. So if you want to just rephrase all of this into a statement to learn, this is how you would write it. 1 mole of any gas at STP. We don't have to describe STP. We know it means temperature 0, pressure is 1. Occupies a volume of 22.4 decimeter cubed. So if you're learning this law, this is basically what it tells us. Right, and now we're going to put this law into practice to see how does it look. Okay, so the first thing we're going to do is we're going to take a very simple equation, and I'm going to explain what this means, and then after we do the chemical equation, we'll then go on to how do we balance these equations. So let's say, for instance, we were given this equation here. So let's just firstly take a pause and let's understand what are we looking at when we are given an equation like this. What do we need to check for? The first thing we need to check for is that is this equation balanced? Okay, and how do we set this up? Well, as we said from the first lesson, we always have products on one side, reactants on another side. So we look at where the arrow is and we draw a line to divide the products and the reactants. Then we write down every single element we can find in the equation. So on my left-hand side, or my reactant side, which is here, products are here. On my reactant side, I can see that I've got Fe and I've got oxygen, right? And then on my product side as well, I've got Fe and I've got oxygen. Now we're going to do a count of all the molecules on the reaction side first and then the product side, and we're going to compare. We know from the first lesson that we did, we must always have a conservation of mass or a conservation of atoms. Today we're going to be checking for the conservation of atoms, right? So we're going to look at Fe and we're going to count how many reactants do I have on this side. Well, I've got a coefficient here, which is a 4, a big fat 4, and therefore I have 4 atoms or 4 moles of Fe. If we look at oxygen, we've got a subscript. Remember, this is a subscript 2. We take the coefficient, which is 3, and we multiply by the subscript 4. So 3 times 2 gives me 6. So I've got 4 Fe and 6 oxygen. Let's look on the other side in our products for Fe. So again, I can see that I've got a coefficient, which is 2, but I've also got a subscript 2. So if I take 2 and I multiply with 2, I'm going to get 4 for Fe. And then once again for oxygen, I've got a small subscript 3. If I take 2 and I multiply by 3, I'm going to get 6. So we notice here that we've got 4 iron, Fe on both sides, and we've got 6 oxygen on both sides. This means that it is balanced and our equation is correct. If the numbers were not balanced here, then it means that we had to stop, we had to go and balance the equation, and then only we can work with it. That is always your first steps whenever you have any chemical equation in chemistry. But now that we've got a balanced equation, we're just going to go ahead and we're going to see what this means for the law we just did. We've got 4Fe solid Okay, so let's just go back to this law. So not the special law, but the one we did first, Avogadro's law. Avogadro's law is telling us that 1 mole of any gas occupies the same volume, at the same temperature, and the same pressure. Now what that looks like when you put it into a chemical equation is this. Firstly, let's understand what is going on here. We've got 4Fe. So notice you've got 4Fe plus 3O2, giving you 2Fe3O3. Alright, so also we can maybe just write down we've got an iron plus oxygen, all giving us the element iron 3 oxide. Don't worry about this notation for now. We're just trying to understand as much as possible what's going on in the chemical equation. The next thing we can say is all of these coefficients are not here for no reason. They actually serve some purpose. And what we can do is we can say if we've got 4 moles of Fe plus 3 moles of O2, and all of that is giving us 2 moles of Fe3O3. So notice the coefficients are actually related to the number of moles. You've got 4 moles of iron, 3 moles of oxygen, giving you 2 moles of iron oxide. This is going to be a very, very important thing to remember going forward, because when we start doing stoichiometry calculations, this is the most important thing you always start off with. You first start by balancing your chemical equation, and notice only if you balance your chemical equation correctly, then you're going to get these correct subscript values. And those subscripts actually tell you the number of moles you have in the equation. But besides the number of moles in the equation, it also gives you an idea of the mass. Okay, but for now we're going to just focus on the number of moles. So if we apply this to another question, I'm just going to write down another equation down here just to get you comfortable with how this is working. So this was number 1. This is now number 2. So we've got N2 plus 2O2 to give me 2NO2. Alright, so this is the equation given to you. Let's make sense of it. The first thing we're going to do is we're going to check if the equation is balanced. We are separating the reactants and the products. We then write down all the elements we see. We've got nitrogen here, we've got oxygen here. Nitrogen, oxygen. Now we're going to count each of these. Okay, on our left-hand side, on the reactant side, we've got a subscript with nitrogen, 2. So we definitely have 2 nitrogen. For oxygen, we've got a subscript, 2, but we also have a coefficient. So we need to take the 2 and multiply by 2. Therefore, we have 4 oxygen elements. Okay, and on our other side, we can see we also have a subscript here for nitrogen. We do not have a subscript for nitrogen. So all we have is 2, and then for oxygen, we do have a subscript, a small 2. So we need to take the 2 and multiply, and if we do that, we'll get 4. And then now we do our check. We've got 2 nitrogen on either side, it's balanced. And for oxygen, we've got 4 on either side, that is also balanced. Therefore, this equation is correct. We can use these coefficients to make sense of the equation. So what does this look like? Alright, so now that we have this equation and we know it's correct, we can trust those subscripts. Remember, if you don't have a subscript, coefficient. If you don't have a coefficient, it's simply 1. So if we take these coefficients to make sense of what's going on, we've got 1 mole of N2 plus 2 moles of O2 to give us 2 moles of NO2. That is how we make sense of it. Okay. So the last thing we're going to quickly just go over before we look at how do we balance chemical equations is looking at another important formula. And this is a formula for any gas, specifically at STP. For any gas at standard temperature and pressure. That means that you can only apply this formula when you have STP. What does STP mean? STP means your temperature is 0 degrees Celsius, your pressure is 1 atmospheric pressure. And don't forget those other 2 units that you can use. So the important formula we can use for this is N is equal to V over Vm. Right? N is equal to V over Vm. This equation only applies at STP. So N stands for the number of moles. V simply stands for volume. And Vm, remember this is now a special value for volume. We call this the molar volume. Molar volume of a gas. And its value is always going to be 22,4 decimeter cubed. And if we quickly just look at our data sheet, okay, I didn't have the values here, but they would definitely give you this value as well, because I don't expect you to know this off by heart. Okay, so the volume of a gas V must always be measured as well. If we're looking at this one, this must always be in the SI unit of decimeter cubed. And for that reason, we're now going to look at the conversions, because they're definitely not going to give it to you in SI units. If they do, that's good, but always make sure you check that your volume is in decimeter cubed. So here's some useful conversions that you may need when you are faced with questions. So 1 decimeter cubed is equal to 0,001 meter cubed. 1 decimeter cubed is equal to 1000 centimeters cubed. One decimeter cubed is also equal to 100 milliliters. So in case they give you any value in meter cubed, centimeters cubed, or milliliters, you now have to convert that to a decimeter cubed. Okay, and I'm just going to end the video here, and then we'll upload another one, just so that it uploads on time and you guys have access to it. But we'll practice doing these conversions, and we'll also practice looking at this equation. And as I said lastly, we're also just going to look at how to balance chemical equations. So it may look like we're doing a lot of things in this one lesson, and it is a lot of things, but just please bear with me, because at the end and by next week, all of these concepts are going to tie together, and you're going to see how it comes together in the exam paper, where they'll test you on these basics. So what I'm trying to say is you're not going to see a whole question, telling you to give something like this or get this value, but rather it will be in a whole question on its own. So today, in other words, what we're doing is we're building up the basics. Okay, so I'm going to end the video here, and then we'll start another video which will be uploaded after this.